Richard Feynman was a scientist who received the Nobel Prize for his contributions to quantum electrodynamics, and his work even helped to create the quantum field theory ideas. So what do you do that was so significant? Well, for starters, he created Feynman diagrams. You see, many people have a hard time understanding quantum physics because of the small level in which it occurs. We talk about very small things such as leptons and quarks and bosons. Well, looking at those things is sometimes really difficult. However, that's not always the case, thanks to Richard Feynman and his Feynman diagrams. To start with, Feynman diagrams tell us how particles interact. Take, for example, these magnets. Everyone knows that if you take two magnets with the same charge and try to push them towards each other, they'll go apart. The closer you get them, the further they want to move apart. And so that's how we have arrows going into the interaction and arrows going out. Notice that since we're talking about interactions, distance is on our x-axis and time is on our y-axis, giving our paths diagonal appearances. Think about it a little more though. How do the magnets know to repel each other? It's because there's an exchange of information or of energy. Obviously, because we're talking about magnets, the fundamental force is electromagnetism, which is why these two particles, which are interacting, are electrons. The force-carrying particle for electromagnetism is the photon, which is represented by this squiggly line. This all seems fairly simple, so why are Feynman diagrams so important? For one thing, we don't actually know how particles interact. We know that this photon is transferred, but we don't know how that happens. For example, before the interaction, maybe this electron emits and reabsorbs the photon. Or maybe during the interaction, before and after it, this electron tossed a photon up and caught it back later. Or maybe even, instead of one photon being transferred, two photons are transferred in this interaction. Any of these combinations is feasible, and there's many more. So, as you can see, there are many ways for interactions to occur, and finding the probability of each event is actually what some physicists do at their jobs. Feynman diagrams allow them a useful tool for not only finding what these probabilities are, but also actually calculating and keeping track of them. In fact, some of this stuff actually propels the work that's being done at CERN and the Large Hadron Collider. Even more revealing is the math behind Feynman diagrams. We can determine numerical values for the force involved when we understand these diagrams and the complex math that comes with them. For example, if we have our two electrons, our two particles, and we know the momentum of both particles going into the interaction, then the force, which is the electromagnetic force for us, can actually be calculated. This is how you would calculate the magnetic force. So Feynman diagrams allow us to actually calculate fundamental forces, which helped quantum electrodynamics to develop. What makes Feynman diagrams so important for physics as a whole is that it explains all the fundamental forces in particles, not just one or the other. So, let's look at weak force, which is responsible for nuclear decay and explains how the sun works, which is obviously a big deal for us. And we can actually represent weak force through Feynman diagrams. What happens in some cases with weak force is that a proton decays into a neutron. Now, a neutron is a neutral charge and a proton has a positive charge, so obviously something happened. Some force was applied. And we know that that is going to be the weak force. One of the carrier particles that carry the force through the weak force is the W plus boson. A boson is just a force-carrying particle. What happens is after this force-carrying particle appears, it quickly decays into a positron and an electron neutrino. For our purposes, think of this neutrino as being similar to an electron, but with much less mass and no charge. This positron can be considered to be similar to an electron in that it has the same mass, but it has a positive charge versus the electron's negative. So, as we can see, Feynman diagrams explain the particles and forces that make up our world on the micro level. However, there is one force that we can't explain with our current models: gravity. Luckily, scientists are working on that through developing theories such as string theory. For example, string theory proposes that everything, even the most basic particles like the ones we talked about, are made up of even smaller strings, and the different oscillations of the strings make up different particles. The beauty of Feynman diagrams is that even if this is the case, or if there's some crazy new inventive way to look at the universe that explains all of these things in much more detail, Feynman diagrams can still be used to represent, understand, and interpret those interactions. Who knows? Feynman diagrams may be the tool that allows us to develop the first theory of everything.